Okay, yeah, so hello everyone. Welcome to this lecture. I know that uh, it's quite late in the night, probably for most of you here. But yeah, glad to be here. Today I'll be talking about data availability and what it is. Um, yep. So to begin with, um, what is data availability, right? So in order to begin with that question, we need to understand the data availability problem, and then we'll slowly go into how the blockchain space is tackling the DA problem and how they're solving it. There are multiple approaches to solving this problem, and we will deep dive into that a bit more in the session. So essentially understanding the DA problem, right? So the basic question is, how can peers in the blockchain network be sure that all the data in a block is actually available? So the why is that important is because how do we know that there are malicious transactions within a block, or if we don't have the data itself to check it, right? It's pretty self-explanatory because blockchain. So if you think about it, the only way a blockchain can actually work is if you have that data of transactions to check against the current state of the chain, right? Only then can you basically reconstruct the state of the chain, or you can identify if there's any malicious transaction in it, right? So it is very critical to the security of the entire system. And there are different ways in which the DA problem is solved, and it is very core to the blockchain stack. Like when you're talking about blockchains, the DA problem comes inbuilt with it. But you might have heard the DA term being coming up in the past couple of years, maybe in the past year, more frequently than before, because of basically the modular movement, right? Because people are talking about decoupling different layers of the blockchain stack. That is, we'll get into that a bit more, but essentially, we've been so far been involved in monolithic blockchains, which means all of the execution, all of the settlement and the ordering and the data availability was handled by the chain itself. But we've now quickly realized that it's much easier and much more scalable if we can decouple these systems and kind of have each layer focus on itself rather than having a coupled system that focuses on everything at once, right? So we'll go into that a bit more. So that is where the DA layer comes in. A DA layer is a blockchain or some system that is hyper focused on data availability and allows rollups and app chains to submit data off chain in a cheap and secure fashion, ensuring that the data is made available. So let's just see how data availability works in the real world, right? So basically, the main use cases of DA comes in, and it's usually seen in ZK rollups and optimistic rollups, or basically in rollups in general. Basically, in ZK rollups, if you think about it, right, you need to access the transaction data in order to recreate and advance the state. So how ZK rollups work is you have some users coming in, sending some data, or probably the sequence is the data, it is being executed, the proof is being generated, the proof is being sent to Ethereum, for example, right? But the thing that you have to understand is that the proof alone does not mean anything. You need to have that transaction data, the differentials to be able to make sense of that proof, right? Um, Even for optimistic rollups is the most, I think, the easiest thing to understand here. Like you have some sequencer that is collecting all of these datas, the transactions actually, and it sequences it and it batches it together and sends it. It updates the state and sends it to Ethereum. And without the data, transaction data itself, you are not able to identify if there is some malicious activity going on, if there is any dishonest state being proposed, right? So yeah, this is basically what I was talking about of the ZK rollup. Suppose Alice is operator of a ZK rollup and she submits the ZK proof on Ethereum, which is verified. The proof is verified, obviously. But if she does not submit the transactional data on Ethereum, although the proof proves that the state transitions are valid, you are still not able to get clarity on the actual state itself, because, well, it's just think of this, right? So you can create a ZK proof that basically verifies that some computation was done correctly, but you don't really get information on what computation was done correctly, right? So that is the nature of ZK, and that is why we need the state, the states to be sent, or basically the transaction agent state diffs to be sent to the L1 layer or a DA layer, if you say so, right? So if you can see in the diagram as well, the users are sending transactions, the transactions are being batched, the proof is being sent to the L1 as well as the batch is being sent, right? Pretty straightforward here. Same thing for the optimistic rollup as well. So it's being batched. If there is a fraud proof, you need to create this fraud proof in an optimistic rollup. You need the transaction data, right? Otherwise, you're not able to create the fraud proof at all. So I hope you guys have understood what the DA problem is. If you have any questions, you can obviously type it in the chat and I can get to it as I move along. So here's a very quick simplified view. So you have a roll up that is creating all of these batches, it's executing these transactions and all of that, and it sends the proof of execution and all of that to some settlement layer and a DA layer, and the DA layer basically ensures that the data is available for the execution or the settlement to take place, right? So that was the problem. So we kind of understood already that we need data, we need the transaction data, we need the state differential data for rollups in order to in order for these rollups to work properly, in order for blockchains to work properly. And basically, if you hide this data, uh, there is no security guarantee that the chain works, or the data, the executions that was done, the computation that was done is correct, right? So how do we solve this? So there are basically four approaches that we can see right now in the space. One is the monolithic approach, that is obviously the execution by full nodes. That is basically all of the execution, the data availability, the ordering, everything is done on one chain. So this is what Ethereum does. This is what Solana does. This is what probably Sui does, right? If you've interacted with these chains, they are basically just monolithic chains by itself. If And they take care of all of the activities there, right? The full nodes get all of the user transactions, it executes it, and the block producer produces the block, the data is being put into the block, and the block is being propagated throughout the network, right? And if the data is not available, or if the state transitions are not valid, the full node, because it has all of the data, it can reject the block, right? So this is very crucial, because the full nodes are able to do both the execution and the data availability in there. They're able to reject state transitions that are not valid and only accept correct blocks, right? So this is how a normal blockchain works. That's why I said that in a monolithic architecture, this is hidden away, because it's just core to how a blockchain would work. You need the data to be available, right? But now where things start to change is when Ethereum had started to not being able to scale. It was not scaling properly, right? It could not handle the amount of demand it had, and people started creating rollups. Rollups are essentially just off-chain execution. You are basically doing execution of transactions somewhere else. You don't have to know where it is happening. And whatever at the end of the off-chain execution, whatever state that execution has achieved, you want to prove that it is done properly and that state is valid, and you're sending it back to Ethereum, right? So that is what rollups do. So many rollups today use this approach called as so they use on-chain DA. So they basically use something as call data or blobs. When they do their off-chain execution, basically they send their data back to Ethereum through call data. So I think in March, there was a Denken upgrade where they implemented EIP 4844, which introduced a concept called as blobs. But previously, rollups used to send data through call data, which is very cheap to do, but it still bloated the network, and gas fees was pretty much very high always because of that. And there was a lot of demand. And the EIP 4844 introduced us a new type of transaction called as blobs. And basically what it did was it was introduced into the consensus client of the Ethereum, whereas call data meant that call data was on the execution client. So those are different clients. Ethereum has multiple clients. There's a consensus client and there's an execution client. Basically, what it achieved was it reduced the amount of fees for sending data to Ethereum. So rollups could now use blobs. They didn't have to fill up the transaction, the transaction pool through call data. They can now use these blobs to send data in a much cheaper fee, right? And this introduction of blobs was called as prototype sharding. And what is prototype sharding? It is the precursor to what Ethereum calls dank sharding, which is their roll-up centric roadmap, which is one of their end goals in their roll-up centric roadmap, which basically allows more space for transactions and also to introduce a much more matured blob ecosystem. Basically, instead of providing more space for transactions, Ethereum sharding provides more space for blobs of data, which the Ethereum protocol itself does not attempt to interpret. This is because, like I said, you just need to submit data. It doesn't have the Ethereum protocol itself doesn't have to interpret what that data is doing, because at the end of the day, this data is being inferred by smart contracts and stuff. Ethereum itself doesn't have to do any execution or do any state changes for the data itself, right? And this will help support L2 rollups for high throughput transactions. So the main thing that dank sharding will eventually, so it's still it's still 3 or 4 years away from us. Proto dank sharding was just implemented. Full dank sharding is probably years away from us. But the main feature that it kind of brings is the merged free market, which means that instead of there being a fixed number of shards on the network that are creating their own blocks and all of that stuff, you have one proposer that is choosing all the transactions and data that is going into that particular slot at a time. This is done through something called as proposer builder separation, and block builders carry out. So basically, proposer builder separation basically means that you have two kind of participants in that network right now. You have a block builder and a block proposer. The block proposer proposes the transactions, and the builders build the block, and they both work hand in hand, and the validators just have to verify that the blocks are valid, right? And they can do this through data availability sampling, and we'll go into that a bit more. Essentially, this is just a diagram of what that means, right? Basically, you have the blobs. Blobs are being sent to the Ethereum beacon chain. This is the consensus part of the network. Nodes can download the entire block data, or if they don't want to, they can do something called as data availability sampling to verify that the data is available and it has been properly sent to the network, right? So the problem with this approach is that previously, before we had the proto-dank sharding, before we had blobs, 90% of a rollups cost was sending data to Ethereum. So if you've used Optimism, Arbitrum, zkVMs of any sort, what you may have known or may not have known is 90% of that particular rollups operational cost was sending data or this transaction data back to Ethereum via call data. And this is why blobs were introduced, right? But the problem is that if the demands of rollups keep scaling as it was in 2023, which was 16 times since the beginning of 2023, then we will soon reach pre-proto-dank sharding levels of fees. So a one-time increase or a decrease of fees is not going to be helpful. So what is the obvious next approach that we can do? One approach is obviously off-chain DA via a data availability committee. And a data availability committee is basically just a centralized subset of validators or nodes who basically say that, hey, I'm going to keep this data. I will make sure that this data is available. And I'll keep it on my centralized storage. I'll keep it on my side. And when you want this data, if you want to check if I have the data, you can simply ask and I'll show you. So basically, this is a very centralized form of off-chain data availability. So the difference here is data is being made available on like if you're using call data or blobs, you're making sure the data is being made available on chain. Whereas in via data availability committee, you're keeping this data off chain. And if you want to use it or if you want to check this data, you need to ask the person who is holding this data to give you the data to you. Whereas on Ethereum, you don't have to ask anyone, it's there on chain. You can use it by yourself, right? Basically, you're trusting a group of nodes who have some monetary or reputational value at stake. So these players might have some tokens at stake, or they might just be, big organizations or big validator groups that have reputation at stake, right? This is the cheapest form of DA, but obviously cheaper does not mean it is safer. There's obviously a risk of security here. And so what is the next best approach? Next best approach is obviously a decentralized blockchain DA layer, which uses our data availability sampling. It may or may not use it. So the best of both worlds is that we have some kind of an off-chain DA layer that can give you cryptographic and cryptoeconomic DA guarantees. So DA layers are usually blockchains uh, that are hyper-focused on enabling data availability. They have these specific features and modifications made on their protocol level layers that allow it to provide DA guarantees. For example, Avail DA uses validity proof technology using KZG commitments and light-line data availability sampling to ensure that the data stays available on the network. So when I talk about data availability sampling here, right, what does that mean? What I've been using the term data availability sampling and data availability. So data availability is obviously, I've explained what data availability is. So what does sampling mean? What is the sampling that is being appended here? So basically, imagine you have a client, but the light client, basically what it does is, in a conventional sense, it just takes block headers. It does not download the block data itself. So how can you ensure that that block header is valid or not? So basically, data sampling works by probability. Basically, you have a light client uh, that says that, okay, I'm going to sample, or it doesn't even have to be a light client, it can be a full node as well, or any node for that matter. Basically, data sampling means that you're going to fetch random small chunks of data. You're not going to download the entire block. You're just going to ask maybe 10 bytes of data, or maybe a few KBs of data, or a few bytes of data here at random points in the block. And if the node is able to give it back to you at each and every single time, your confidence increases that node has made the data available. So if you look at this picture, I think it explains it really well. So if you have a box of multiple different balls, right? It has a couple of different balls in there, and you want to ensure that there are, for example, only um, you know okay, you want to ensure that only valid blocks are there. So each time you're picking data from this box, right, what happens is, so you either have it or you don't have it. So the probability for you to have it is 0.5. Like, if I have no information, the probability is 0.5. So the first time I randomly sample some data, there's a 0.5 chance. But then if I again sample one more time, this is 0.5 into 0.5% chance, right? And the more times you do it, the higher probability that node or that entire block data is available, right? If you fail even once, it means that entire block can get rejected. So it's a kind of a tricky concept to kind of wrap your head around, but once you get it, it's pretty cool to see. It's basically mathematical probability around which you can scale blockchains, and you can with high confidence say that this block data is available. And this is if there's only one light client or one node just sampling. Imagine there's multiple nodes or multiple light clients sampling at the same time. You are, going to be 99 or 100% sure that, that data is available, right? And this scales well because as block size or data size increases, you don't have to increase the number of chunks that need to be sampled, hence making the resources needed for LCs very small, right? Um, yeah, for example, in the case of Avail has a P2P network of light clients randomly sampling data and verifying that the data is available by checking against the KZG commitments in the header, and we'll go into all of that pretty soon. You don't have the advantage of this is that you don't have to trust a validator set. So if you have a light client doing data availability sampling, you don't have to trust a validator set for the availability of data. Once enough light clients have sampled data, so in the case of Avail maintains a distributed hash table so the more you sample data, it is being stored into a distributed hash table, which is being maintained by a P2P network of light clients. So imagine there is like 1 million light clients in that network, and they're all managing this distributed hash table. And if you're sampling different small chunks of this data in a block, imagine if there's a millions of light clients sampling the same block, there will be a point of time where almost the entire block will be sampled at one point of time. And because of that, the distributed hash table is able to create a block replica. So even if the entire network or the RPC network goes down for Avail, you are not losing your DA guarantees up to that point, because you can always fetch that block again. The block replica is able to be fetched by the P2P network of the light clients, right? So this is something cool that Avail provides. So what makes a DA blockchain different from a normal monolithic blockchain, right? Essentially, um, a DA layer is focused on DA and does not have a custom execution layer. So if you talk about Ethereum or Polygon, or you have any other rollup or any Solana's elements like Solana or Sui, what they have is they have an execution layer. They have an EVM, they have a Solana VM, they have a Move VM, okay, they have a ZK VM or whatever. They have some kind of execution engine that allows you to code smart contracts and deploy these smart contracts and have some kind of function happen because of the functions that are because of the code that has been written and being executed by these virtual machines on this chain. But on a DA layer doesn't necessarily need to have an execution layer. It can this is the reason because of this is essentially you can have any execution engine be built on top of Avail DA or any other DA layer for that matter. And basically, whatever execution is being done, you can send the data to Avail or to that DA layer, and ensure that the data is available. So it does not have to be opinionated on any kind of VM it chooses. It can, so a ZK VM can use a DA layer, a WASM can use a DA layer, and EVM can use a and a DA layer, right? And it does so because it does not infer the data that is being sent to it. It can remain a DA layer can remain neutral. It can be credibly neutral and unopinionated, right? So how does an off-chain DA layer uh, how is this DA problem being solved by an off-chain DA layer, right? Because data unavailability is not a uniquely attributable fault. This means that participants cannot prove to other players that a particular chunk of data is missing. Okay, let's so basically what that means is, if, for example, right, let's just consider there is this is basically the DA problem all over again, right? So you have Bob who has some kind of the block data, and Alice is requesting this block data from Bob. So Bob might have done something malicious on that. He might have added some data that is not supposed to be there, or he or she might be wants to hide some data away from Alice. So what Bob does is Bob hides that particular amount data, and sends the remaining block to Alice. So since Bob is sending this data with which has some missing data on it. Sorry, since Bob is sending this block with some missing data, Alice we can reach out to Charlie saying that, hey, I think there's some data missing. I want to create a I want to create a complaint or something like that. But Bob can essentially send this missing data to Charlie, right? For example, it can make, so for example, let's just say that Alice requests a block from Bob, but the data is missing when Alice receives that block. Alice complains to Charlie saying that, hey, I think, you know, there is something going on here. And if Charlie requests the same block from Bob, since Bob does not want to get in trouble, Bob can add this missing data and just send the complete data to Charlie, making Alice seem like the bad actor here instead of Bob, even though Bob is the bad actor, right? And this is a problem because we do not want the bad actor to win. We want the not bad actor to win, basically, right? So how do we solve this with an off-chain DA layer? Basically, let's think about it from scratch, right? So full nodes sync upon the entire block, right? They spend resources to check transaction validity and stores the block in. Light nodes, for example, they just receive the headers without syncing on the block data. There's no way to verify the data is available. The only way they can know how to reject a block header is that if the full node sends a fraud proof saying that, hey, this has something going on, this is the malicious block, please reject this header, right? But light nodes face a problem. If the block producer does not reveal the entire data behind the block, the full nodes will not be able to create um, a fraud proof because it does not have all of the data required to create a fraud proof. So Lightlines have so the Lightline thinks it has the correct header and it will accept that malicious header, right? And basically it will accept that malicious block. So to counter this, we need a mechanism for Lightlines to verify data availability. So an example would be, suppose Alice constructs a block B with transactions 1 to n, and let us suppose transaction 1 is malicious transaction and it is broadcasted, right? Any full node can identify that it is a malicious transaction and reject it. But if Alice wants to hide transaction 1 and reveals the header and all the transactional data except transaction 1, the full node cannot basically create that fraud proof telling the light node that, hey, this is wrong, do not accept this header. So hence, um, we have no way of basically conveying to the light node saying that, hey, this is basically malicious. So one way to solve this, you would think, is light client, because we just discussed about data sampling, a light client can just simply sample random chunks of data to ensure availability, right? Simple, that's a simple solution. The problem is, if there are n transactions in a set, there is a 1 by n probability of that unavailable data to be found. Because if there is only one, so for example, one light client, if you are running a light client on your device, for example, um, there is a 1 in n chance for you to find that to find out that this data is not available or this block is not valid, right? So you might only sample 5 positions of 5 chunks of data, for example. So what if I sample this small chunk, this small chunk, this small chunk, this small chunk, and this small chunk? I'll think that the entire block is valid. But this data is unavailable here, right? So this red part is, for example, imagine is unavailable. So how we can solve for this is basically redundancy. This is done through erasure coding, which is a mathematical way of basically kind of ensuring redundancy in data. Basically, if you have some data of n size, you can create 2n chunks of data uh, uh, in such a way that you just need n chunks of the 2n to reconstruct the original piece of data. You just need access basically to any. So if you are basically erasure coding here, right, in this blocks here, basically imagine this data is erasure coded. This previous block is erasure coded to 2n. So if there are n transactions here, you have now 2n chunks here. And what you just need any n. Basically, you can have any n of the total 2n chunks or transactions to reconstruct the entire block. And that is the magic of erasure coding. And the same basically, and it's not like a new technology, it's been used for so long, like for years. I mean, if you've used CDs, for example, CDs use erasure coding on their disk. That is why, like, you might have seen, like, if there is a small scratch on your disk, on your CD or DVD, it still works when you put it in the DVD player, because there is redundancy of data. Even if you lose some of the data through scratches on that CD, you can still get almost all of that data without losing the original data, right? So this is what erasure coding is. And the beauty of it is that because you just need n out of 2n data points to get back the entire block. If someone wants to hide the data, they have to hide n+1 data chunks. They have to hide n+1. So they need to hide a block, a complete block, and one more transaction in order to completely ensure that some data is not available, right? And this is hard to do. This is hard to do because now if you're randomly sampling data, there is a high probability that you'll understand that some data is not available, right? So basically, imagine you have some transactions which are basically, imagine you have a matrix of data or matrix of transactions, and you are basically erasure coding it or extending it like this. So in the case of Avail or any DA layer, they create some kind of a commitment and add it to the block header in order to ensure data availability. Basically, you erasure code data to ensure redundancy of data, and this helps in making it difficult for the block producer to hide data, or any node to hide data from you, because they will need to hide n+1 data chunks in order to ensure that the block data is not completely reconstructible, right? Um, and this ensures that light client has very high confidence in the underlying data is available. And this diagram basically shows that entire process. And we'll come back to this real soon. Essentially, does this solve the DA problem? Does doing data availability sampling and erasure coding solve the DA problem for an off-chain DA layer, of course? Because if you are obviously having a monolithic chain, most of this doesn't matter because all of it works already. But for an off-chain DA layer, does this make sense already? Have we solved it? No, we have not. Erasure coding can be done incorrectly. Intentionally or not is another question, but erasure coding can be done incorrectly. And if erasure coding has been done incorrectly, then there is a problem again, right? So although the simple trick makes the job of hiding data more difficult, it is still possible that block producer just intentionally performs erasure coding in a wrong manner, hence making sure that, whatever you've guarantees that you think you have is wrong. So a full node can obviously, again, verify this erasure coding was incorrectly or not by re-executing this from scratch, re-executing the encoding again, and ensuring that, all of it is done properly. And if it is not done properly, you can create another fraud proof, just like in the case of malicious transactions before, right? So interestingly, in the case of DA, though, you just need one honest full node to be certain that if a block is malicious, then it will receive a fraud proof. Because if there is one full node that is honest, and it does the encoding correctly, and it finds that the encoding is wrongly distributed, it can create a fraud proof and send it to all of the other full nodes as well as the light clients, right? So there is a fraud proof guarantee there as long as there is one single honest full node, right? DA layers like Celestia use this fraud proof approach, but like we have always mentioned already, fraud proofs can be inefficient. It does not give you a succinct or proper guarantee that it is that data is available, or if the encoding has been done properly, and all of this, right? Because what if there is no one single honest validator or one single honest node or whatever, right? It is always a point of doubt that comes in there, and this is why validity proofs are much better. And even in the fraud proof case, light client always need to trust the full node to be honest, right? And honest nodes need to be incentivized to keep being honest, right? And this is the problem of being a fraud proof centric approach. And Avail solves this using validity proof technology. So a validity proof based solution enables applications to use a system without having to wait for fraud proofs, right? Avail uses uh, Avail is the only DA layer that uses KZG commitments, and Avail DA is able to commit to a polynomial using a single elliptic curve group element. It is the same commitment scheme that Ethereum plans to use for the danksharding roadmap, a block. So basically what it does is, and now I'll go to the previous diagram that I was about to show, where a block can be encoded into a extended matrix of n to m rows, rows and columns, obviously, and each row of this extended matrix generates a polynomial commitment. So basically in each row, you're creating a polynomial commitment and send these commitments as part of a block header. And I'll just show you the schematic representation of this. And light clients can now query any cell of this matrix to open it against the KZG commitment and check that, okay, because of the KZG commitments, now you're sure that the erasure coding has been done properly. And when you're doing the light line data sampling, you're able to fetch the data, check it against the KGG commitments to ensure that everything has been done properly in a validity proven method, right? And if I go to this previous diagram here, you can see that happen here. So basically you create a matrix of the data or whatever chunks of data in cells, basically, and then you extend the data, or you basically erasure code the data and create this extended matrix of n into m size. And in a row-wise manner, you create a commitment saying commitment for this row. So for this row of cells, you create a commitment. And for this row of cells, you create a commitment, and so on and so forth. For the entire matrix, you create a commitment and make it part of the block header. So because of this, now you're able to verify when you're doing data availability sampling that, hey, because I have data from, for example, D2 2 and 2, I can check against this commitment and open this commitment and check that this data is valid and all of this is correctly done, right? And that is the magic of validity proven technology and KZG commitments that Avail uses, right? Yep. So yeah, this is how that entire life cycle would look like, right? So you have the original data, you have the erasure coding and extended data, you put it into the header. So, and now the entire block would look like the header with the data and the extended data all together. And you propagate the block to validators who verify the block. And then uh, you have the blockchain here, right? And we reach consensus on the block order and all of that. And then what happens is, now that you have the blocks, the light client network can do its job of doing data availability sampling and ensuring that the data is made available without trusting the full nodes. You don't have to trust a fraud proof coming from a full node, because now the light client, that means, which can run on your phone or your smartwatch or your browser even, can directly look at the blocks, verify that the data is available without relying on a full node, right? And this is where magic happens. Um, so we are able to minimize trust and increase decentralization in a way that no other approach could uh, do, right? And that is what the data availability solves. We want to be able to have cheap and secure DA without compromising decentralization and security that a monolithic chain would provide, right? Or submitting data directly on chain to Ethereum could provide. But even though that is secure, it is costly, and costs also come into the factor for all of these rollups. And how can you have cheap DA and secure DA? That is what these DA layers allow you to do. This is again another diagram that kind of shows the data, the extended data, that the commitment being sent to the header, and this DA layer is basically creating blocks, which is being used by applications, and the DA layer is basically underneath all of the execution part of it. This diagram again just shows through all of the different kind of constructions you can have. Monolithic chain, Ethereum rollup without any other DA layer like call data or blobs, or if you use a DA layer like Avail for data availability, you can create a Validium or a sovereign rollup and stuff like that. And the last part of this lecture, I think I'll quickly close off. So we have the DA, guarantees from this off-chain DA, but what if you want to attest to this DA guarantees on Ethereum on chain, right? So to ensure that the data was available, made available, L2 state validating bridges are created on the settlement layer itself, and it provides a proof saying that okay, this data was sent and this is the proof of the inclusion, and this ensures that to prove that the data was made available at somewhere off chain, right? So should L2s publish data directly to Ethereum in forms of blobs or call data? This is inherently satisfied because the data is being posted on chain. But if it is using an external DA provider like Avail DA or any other off-chain DA provider, then a data commitment needs to be posted to Ethereum. In this case, Ethereum must be convinced that the full data was indeed made available, and this so-called DA bridge is attesting to that fact, right? Basically, if you look at this diagram which I took from L2B's recently released DA risk framework, basically you have a bunch of users sending transactions to a sequencer, and the layer 2 has two approaches here. One, they can send data directly on chain, which is, so for example, Ethereum, for example, it can send directly the data to Ethereum, who is also acting as the data availability provider here, and Ethereum is also acting as a settlement layer. So this data on chain can be sent as call data on the execution layer or as blobs on the consensus layer. Alternatively, the sequencer can send this data off chain to a dedicated blockchain like Avail, or an off-chain committee like a data availability committee that we discussed, right? And the attestation of this data being sent can be created and sent to the DA bridge, and it is stored on the settlement layer like Ethereum, right? So this is how, for example, an optimistic rollup would look like with a DA layer. The transactions are being sent to a sequencer. The transaction data is the sequencer does the ordering. The transaction data is being sent to Avail or any DA layer for that matter. The block reference or the is being sent to the sequencer. The sequencer sends the block reference to Ethereum if it wants, and then the attestation is sent by the attestation bridge to Ethereum. So here, because you just have the block reference and a root and a data root, the cost of sending this root or this basically proof or whatever you want to call it is very small, because it's a very succinct amount of data. It's not a huge amount of data. So you don't have to, so if you're sending this transaction data that might be MBs of data, to Ethereum, it is going to be very costly, but here you're just sending some KBs or even much lesser amount of data to Ethereum. So it reduces your cost, all the while ensuring that data is available. And for a ZK rollup, again, how this would look like is the settlement is done on Ethereum. The proof is probably being sent to Ethereum here, but the transaction data, the state diffs are being sent to a DA layer, and the attestation of that inclusion is being sent to Ethereum. I have added some reading materials here that you might want to check out as well. And yeah, if there are any questions, I'm happy to answer them. I hope that this was, I know it was a lot of information at once, but like, yeah, if any questions are there, just ask me and I'll help you out as much as I can. Yeah, any questions?
Yeah, so a question I have is that these validators are a part of the DA layer that are actually holding this data. Do they hold this data indefinitely or do they hold this for a particular time period?
Depends on how you want it. So you don't have to the validators. So for example, Avail has a validator in Avail. For example, the validators have the option to prune data after I think 18 days or something, because the reason for having this random number 18 days is like because most optimistic rollups their challenge period is like 7 days maximum. And you don't really, and for ZK rollups, for example, after 18 days, like, you can basically create a proof saying that, okay, all of this is already made available and it has been proven, and you can just create a succinct proof again, aggregate that proof or something like that, and you can submit it again or whatever you want to do. It's basically based on how that rollup wants to um, have their security guarantees and all of that. But a DA layer can choose to keep that data or prune it away. Most DA layers will choose to prune it away because after a point of time, maybe like data from 6 months ago or like 1 year ago is not going to be relevant anymore. It will probably be pruned away and won't be kept on chain, because the entire point is not to keep it as a data storage mechanism. It's a data availability mechanism. So you just need it for a short span of time, and once a particular time amount of time has passed, you don't need that data anymore, if that makes sense.
Okay, so like if you opt to prune the data after like a sufficient period of time, what if I want to access that data? So like how would you ensure that if the nodes are pruning the data, then the data is not lost?
Pruning means you lose the data, right? So if you want to, at some point of time you want to keep that data, so every network has this thing called as archive nodes that kind of keep the entire state of the blockchain, right? There are archival node solutions. If you are a roll up, for example, suppose you are an Polygon, for example, right? If you're Polygon and you have a rollup or a Validium running with data being sent to a DA layer, and you as a customer of that DA layer, or you as a rollup on that DA layer, don't want to lose the data, you can choose to run that archive node, or you can choose to hold on to that data for a longer period of time by storing their data somewhere else, right? But as a DA layer, a DA layer's job is to just keep that data for a small period of time to ensure that the whatever data has been submitted, you have enough time to check against whatever execution has been done. And so like maybe 1 year, like, I mean, obviously 6 months later or 1 year later, whatever transaction happened 1 year ago is not immediately, it's not going to reorg anymore, right? That data, whatever transactions happened 1 year ago, is not going to reorg today, right? So if it does reorg, it is going to be a big problem, right? That is another discussion to be had. So that is the uh, basically that's the gist of it.
Yeah,
Basically, the project can, if anyone can store an archival node if they want to, but like over time that cost of storage is going to be, GBs and TBs of data will eventually, over years, it will accumulate. So you'll want to eventually prove some data away, which is not needed.
yeah, okay, that makes sense that you might not want to keep data for a long time because yeah, the chances of reorg decreases exponentially. But like you might want the historical data for some data analysis or stuff like that. And as you said that anyone who wants to access data can query these archive nodes. But it is obvious that these archive nodes they have huge storage requirements. So there would be like far fewer archive nodes than there are these validators and full nodes and light clients. So, do you think that this can create a sort of decentralizing problem that there are only few archive nodes that have the entire chain state from Genesis, and that could create maybe issues that you have to depend on such a small set of data storage nodes?
I mean, that's a good question, but the thing is, again, what is the centralization risk here, in the sense for data analysis? I mean, what is the centralization risk in a data analysis perspective, right? The guarantee you need is that when the execution happened, nothing malicious happened. Like data analysis may, like, what is exactly the guarantee that you need? Like centralization, decentralization, like, doesn't really matter at that point, to at least to me. But that is a valid question, and it can be solved by decentralized storage networks. Like you can use IPFS to probably send data for long-term data storage like Filecoin. You can use systems like these to kind of work with the DA layers to kind of create like a long-term block archival system. And Avail is thinking of about solutions like that. If I only know about Avail, I don't know about other DA layers, but Avail is working on solutions for long-term decentralized long-term blockchain archival in a way that you don't have to trust the centralized parties, obviously. So I mean that if that helps.
Yeah, that's really exciting and interesting to know. Another question I had was that these DA layers, they are basically making it very cheap to make data available, right? And they're able to do so because you're doing erasure encoding and you're basically sharding all the data. So like each node in your validator set does not have to hold the entire data, which currently happens on Ethereum, like which happens on Ethereum before the blobs upgrade, and now in the blobs upgrade, there's a different mechanism. So like my question is that after dank sharding happens on Ethereum, where sharding is an inherent feature on Ethereum itself, and there is also another EIP I read about, like I think it's a 4444, where there is a proposal to also prune data on Ethereum as well. So like if these changes are made to Ethereum, then what would be like the difference in costs and what were the economics of Ethereum and data availability layers?
Yep, that's a great question. So one thing about Avail, to just give you a bit of this thing on it. So Avail, and I think also Celestia as well. They don't shard the data among validators. All of the validators hold the entire block data. So you get that guarantee, like the full nodes at least, they hold the entire block data. The light clients can randomly sample data to ensure the data availability, and they also maintain a DHT for a distributed hash table. In case of Avail, the light clients maintain a peer-to-peer network that can also maintain the state of the network, that can replicate the state of the network as well. Now, when it comes to tank sharding and any other future improvement that comes to Ethereum, it is so the basically the question is what is there today versus 5 years later, right? Avail, for example, provides everything that Ethereum's tank sharding wants to provide today, not 5 years later. So that is basically first mover advantage kind of thing. Secondly, obviously Ethereum would be the go-to for many rollups or many projects there, but they'll have to wait for 5 years. And once it does come, there is a lot more improvements that will still need to be done. Even you see, it's not like a one-time solution. Like introducing blobs, everyone thinks is like a one-time solution and it's done, and we won't have any blob like gas fees issues anymore, because no, blob fees is keeping on increasing day by day, like as demand increases, as more roll-ups come. Now imagine the end game here is, or the end vision here is, that rollups are eventually going to be more application specific and not only uh, uh, general uh, chains, for example, or generalized rollups. You'll have application specific chains, and just think of it like a microservices architecture wherein you have specific rollups that do specific things. And if that is going to be the case, you are not going to have like just one or two rollups. You're going to have thousands, or if not hundreds of thousands of rollups being built for specific applications that's going to be tackling that, right? And that introduces the rollup fragmentation concept also. But there's going to be a huge rollup demand, and Ethereum alone will not be able to handle it. There will obviously be need for external providers like Avail, and also there is going to be a need for solutions to basically basically connect all of these rollups in a way that you abstract away the rollup layer, right? You abstract away what rollup you're using, which ecosystem you're using. Are you using ag layer? Are you using OP stack super chains? Are you using some other random chain? Are you using this application specific chain? Nobody wants to know that, right? When you're using Amazon on your browser, for example, you're not knowing, you're switching from Amazon to Razorpay to pay or do your payment, and then you're coming back to Amazon. The requests between these microservices, these APIs are not being known to you. It's happening like in a snap, and eventually we need to reach get this ecosystem to a space to a place where that happens. And Ethereum alone cannot do that. Avail has Avail Nexus that's coming. DA is not the only thing that Avail is working on. Avail has Nexus happening, it has Fusion happening. So Nexus is a way of coordinating multiple rollups. It's a coordination hub which aggregates proofs of state transition functions of different rollups and allows asynchronous composability and atomic transactions between them, allowing them to interoperate in a way that is never possible before. So um, it's not only about DA layers at the end of the day, it is what it allows to you to achieve. Obviously, Ethereum will have that. Like when danksharding happens, it will have users rollups being built on top of that, but there'll always be rollups being built on top of other external providers as well. And also there will be solutions like Nexus from Avail that is going to be able to interoperate and allow the unification of all ecosystems, even Ethereum rollups, even Avail rollups and other ecosystem rollups. Like even if you have Celestia based rollups, they can integrate Nexus and they can interoperate among all of the other rollups in the ecosystem, right? So that's the kind of the end game here. So it's not just about DA, it's about what it can enable, I'd say. Like that's just my opinion there, but yeah.
Yeah, makes sense. Also, another question is that if like Avail validators in of itself are not doing dank sharding, then where is the cost cutting exactly coming from? Because, like, yeah, when you're submitting the state root on Ethereum, that is like it's the difference between a single state root or the entire transaction call data. But the validators of Avail itself, they need to be paid rewards in order to store all of this data, in order to incentivize them to do this. So, like, what is the economics of that?
I mean, so every layer one has its own tokenomics in terms of like how the rewards are being distributed, how the validators are going to be incentivized. I think that is um going to be there for every protocol. So I mean, it's not only about the cost, like I said, right? So there's a lot more to it. It is also about security. It is also about what can be done beyond DA. And for validators themselves, obviously, I mean, for any DA layer, for that matter, even if it is uh Celestia or ICANN or near DA or Avail DA, they're going to have to incentivize validators in some sort of manner. That is probably going to be through a token or through other rewarding mechanisms. So in Avail, for example, the Avail token will be the token that is going to be used at least now to secure the consensus of that network. But we will also bring in what I said. So we Avail DA, there's Nexus, and there's Fusion. And by Fusion, well, like I mentioned, the end game is to unify all ecosystems. And if we want to unify all of these ecosystems, Avail is also going to be able to enable other ecosystem tokens to be staked on top of uh, the DA layer, the Avail DA consensus layer. That means you can imagine that you can stake your Bitcoin, you can stake your Ether, you can stake any other token or any other rollups tokens on the consensus layer to add to the crypto economic security of that consensus layer. So it's not only about um, rewards in terms of the native token of that layer. It's also um, other ecosystem tokens, other ecosystems pooling in and providing their crypto economic security on this consensus layer, which will be unifying like everything together, which is something that I'd say no other layer is doing right now. But yeah.
Yeah, makes sense, makes sense. Yeah, thank you for answering our questions. And are there any other questions from the chat? All right, in that case, I think it's a wrap. Yeah. Thank you, Robin, for taking this lecture.
Yep, I'm happy to be here. Thank you for having me, actually.